Welcome to this morning's Spark and AI Summit general session. Our next speaker should be familiar to a lot of you. Adam Pazske is the author of PyTorch, which has made huge inroads in the machine learning research community over the past few years. Join me in welcoming Adam as he talks about recent efforts to help drive adoption of PyTorch, things like easy model packaging and export, simple mobile deployments, and Python-free execution. He'll also cover the core concepts behind the library as well as upcoming features. So let me hand it over to Adam.
Hello everyone, my name is Adam Pazske and I'm one of the original authors of PyTorch, although this talk really is on the behalf of the whole PyTorch team and really all of the contributors because it's an open source project. And today I want to present to you PyTorch as a modern platform for machine learning research and production. So if I were to describe essentially what PyTorch is using just like one sentence, I would say that PyTorch is NumPy with batteries included. And especially some of those batteries are crucial when it comes to executing certain kinds of workloads, so in particular machine learning. Those batteries, right, those features include things like accelerator support, so you can easily write your code, your ND array code, which essentially, not only can execute on the CPU as it would normally with NumPy, but it can also use GPUs or TPUs or any other accelerator that might become popular in the future. Also, another really important feature is high-performance automatic differentiation. Basically what it does is you only have to write basically like your complicated machine learning model, and the code to compute the gradient of, let's say, some loss function can be derived by the system automatically for you without you having to sit down and actually do the derivation by hand and later implement it in code again, which is obviously very error prone. More importantly, I guess for this conference, the features we will be covering right now are a just-in-time optimizing compiler for ND array code, which also supports code export such that it can actually execute entirely without Python, and also a distributed computing library for PyTorch. So a bit of a origin story of PyTorch is that it actually came from Facebook AI research, and as such, sort of research has always been this driving factor in how we were designing and how we were thinking about the library, right? We were always sort of striving to make it as flexible as we can. And I would say that in research we did a pretty good job. If you look at the implementations of the latest machine learning papers, then in the last quarter, over half of them were actually implemented in PyTorch. So that is more implementations in PyTorch than in all the other sort of libraries combined, which I think is extremely exciting. But ultimately, we sort of had this, we started with research, but research is not everything, right? A lot of this research is done to produce models that are supposed to interact with real world, right? Like you can think of autonomous driving cars as one example. And industry and deployment and actually interacting with the real world is not an area where we did great in the past, I would have to say, but it was really our focus for the past 2 years, and hopefully, as you'll see, we are sort of really achieving a lot in that regard. So when I'm talking about deployment, there are really two use cases I think that are somewhat different, and that even includes training, right? One is embedded devices, where essentially those are often battery powered, and you really want to run with maximal efficiency, with no sort of cycles wasted on jobs which you would normally have to do, such as executing Python, right? So regular ways to use PyTorch, which is just writing Python scripts, that doesn't really scale for those embedded devices. And so we had to come up with a solution for that. On the other end of the spectrum, you have computing at scale, right? So you might be deploying your machine learning solution to a whole fleet of servers, or you might be running essentially large-scale distributed training, which is very popular these days, right? Like previously, people would be training a single network on a single GPU for a few weeks, and now on the same data sets, people can actually, using obviously whole clusters, they can basically train those networks to similar accuracy within seconds or sometimes minutes. So the question is, okay, so we started with this PyTorch Eager is what we call this NumPy-like mode, which doesn't really scale properly to both of those, scale up nor down to both of those deployment scenarios. So our solution to this was to create PyTorch script. And PyTorch script essentially is a whole new programming language. The only different, but you shouldn't really be afraid of that, because the new programming language essentially is Python for the large part, so it uses exactly the same syntax, and every TorchScript function is essentially a valid Python function, and it is exactly the same function. It computes exactly the same thing every time you call it. The only caveat is that it is not all of Python, right? So there are some restrictions. Python is extremely dynamic, and because of this, for example, the Python interpreter is incredibly complex. So we had to actually restrict it in some ways to actually make it, one, more optimizable. So we can do more advanced static analysis on our code, and we can actually, let's say, rewrite certain patterns to make them faster or numerically stable. The other benefit we get from that is that it becomes exportable, such that it runs entirely without the Python interpreter, and we can just use our own lightweight interpreter, as I've mentioned, because the language is so much simpler than the regular Python. But also, caveat here is that, you know, it is a restriction, but it is a pretty expressive restriction. So really, most of the models that I've seen that are written in PyTorch easily fit within the realm of TorchScript, and you should be able to convert those relatively easily. So just to give you an idea of how such a conversion looks like, the code in here is not super relevant, but the general idea is that this is a part of the implementation of a recurrent neural network that you could find in some PyTorch examples. And so there are really two steps you have to do to convert your function to TorchScript. One is you have to add argument type annotations. This is because TorchScript is actually strongly typed, and so it will check that you're not overriding a variable with a value of a different type. But annotating arguments is actually sufficient. The rest of the body can be handled using type inference, and so with this limited set of annotations, it's actually sufficient for us. Also, this is obviously also a benefit for documentation of your code, where callers of those functions will at least know what they should be passing in. And then another thing to do is this small annotation here at the top that says torch.script, and basically what it does is when Python gets there, when it actually sort of creates the function, whenever you put torch.script, instead of creating a regular Python function, this annotation will look at its source, and it will try to verify if the source actually fits in the subset that we decided to, that we can actually support in TorchScript, right? If it does, then everything's all right. And your program functions exactly the same. There's really no observable difference. It should give you exactly the same outputs, no matter whether you have this annotation or you don't. The only difference is that every time you call this function, it doesn't go through the regular Python interpreter. It actually goes through this optimized path, which can do really interesting rewrites, as well as sometimes even code generation at runtime to really sort of produce something very tailored to your particular workload, right? Now, the other alternative is that whenever you put this annotation, something fails. You get an error. And whenever you get an error, this basically means that something inside this function does not really fit into the subset of TorchScript, and the error should basically point to exactly to the place where that happens, and basically explain you why that is and how you should be able to fix it. So, you can see that hopefully this should be relatively straightforward, and as you can see, that should already give us a relatively good path to embedded deployment, right? The workflow goes like this. You write a PyTorch model using regular PyTorch eager, you sort of iterate over it, right? The research is often significantly different from deployment, in that in research you really want a lot of flexibility because you will be iterating on the model, right? And deployment usually is taking the sort of result of this particular, of the final iteration, and actually putting it into some environment, except, at this point it should really run as efficiently as possible. And so you write your PyTorch model using PyTorch eager, you iterate on it as long as you want. Once you're done, you just add those torch.script annotations in a few places in your code, and then using torch.save, you can actually emit like a self-contained package that contains both all of the parameters and all of the state of the model and of the sort of code that is there, along with the serialized code, right? And once you have this package, there are ready-made libraries available on both Maven and CocoaPods for Android and iOS respectively, which you can sort of easily link into your mobile app, and they will be able to actually interpret those packages such that you can easily generate predictions from those models, or even in the future train them. And those packages are really lightweight. It's essentially like just, let's say, 5 megabytes, and that's sort of all the weight it actually adds. All right, so let's move sort of to more of a theme of this conference, which is actually working at scale. So when it comes to deployment, one thing we were really missing, I think, in the past is like a sort of good out-of-the-box deployment solution for web. Now we actually have PyTorch Serve. So that is an official project which essentially can take those packages that either TorchScript produces, or because it runs on like a regular computer, it can also take eager models, in which case it will use Python to actually serve those models. But the nice thing about it is basically for the common tasks like object classification, you basically get like a nice REST API, which semantically makes sense for a particular task and for a particular domain. And you can easily sort of basically in minutes you can get up and running and serving your model to the web, right? And it also supports some interesting features. Like for example, a lot of those models are more efficient if you evaluate them on multiple inputs at once, right? But usually for every single user, you will only be getting a single input, right? So what PyTorch Serve can do for you is it can batch requests. So whenever requests are coming, it can sort of delay them until like a finite time horizon, like a short time horizon, and it can try to like accumulate a few of those in that amount of time, and it will try to evaluate the model on all of those inputs at the same time to better make use of your hardware. All right, so that was like the main thing for when it comes to deployment. I think that was like the main sort of advancement we did. Now let's focus more on the actual like large-scale training. So since version 0.2, that was a really long time ago. Sort of the main way to actually do distributed training in PyTorch was to use an MPI-like multi-controller model. So the idea is that you write a single Python script, you launch it on a lot of different hosts, and all of those hosts sort of evaluate the script as they go, and sometimes they reach something called a collective operation, which is essentially like some data exchange between some of those hosts. And those include like most MPI sort of collectives you might know from different MPI implementations, like broadcast, all reduces, gathers, scatters, point-to-point communication using send and receive as well. And that seemed to work out pretty okay. The only problem with a lot of those MPI-like interfaces is that, well, they lack fault tolerance. And fault tolerance is really important once you really want to scale up, right? So we did a lot of changes in the distributed backend, and that led to PyTorch Elastic. So PyTorch Elastic is exactly this like wrapper around your MPI-like job, which utilizes a Kubernetes cluster. You can either get one on premise, or you can basically rent those from any of the cloud providers. And what it gives you is it provides you fault tolerance. So anytime any part of the job fails, it will restart it automatically from like a well-known state without sort of reconstructing the whole system from scratch. And also another really cool thing, I think, is dynamic capacity management. So you can, for example, use on-spot instances, and whenever they become cheaper, you can actually scale up your training, and whenever they become more expensive, you can actually scale it down without sort of aborting the whole job and restarting it periodically, right? Which I think is also really nice. And also, in case those instances sort of get taken away from you, everything's handled for you automatically as well. All right, so getting back to how you express those jobs, though, in version 1.5, which is the latest release, there's actually a super exciting thing, which I would call a single controller model for distributed. So the difference now is, unlike in the multi-controller model, well, you have a lot of those like scripts which sort of have this distributed control and like sometimes will decide to communicate. Now there's only one Python script actually executing the code, and sort of the rest of the hosts just become sort of dumb workers which await commands from this single controller script. So obviously there are some problems with that, like this single host might become a little bit of a bottleneck for the system. But assuming you can actually like slice off chunks of works that are large enough, such that this single machine might still be enough just to like saturate still a fair amount of hosts. And the API itself is really simple, I would say. It's really just 3 functions and 1 class. Basically what those do is, again, really simple. RPC Sync, you give it a worker name, so that is the host on which, or the process in which the particular computation will be evaluated. You give it a function to evaluate, and you give it arguments. And what RPC Sync does is it will take the arguments, it will ship them to that worker, it will compute the function, it will get the result, it will ship it back to you, and once it gets back to you, it will return the result, right? So it's blocking, this is why it's synchronous. Then there's RPC Async, so that is very similar. It's just that, once it ships the arguments and computes the function, it returns immediately. It doesn't wait until the data comes to you, but the data will come to you automatically as well. The only difference is that RPC Async actually returns something called a future object, which essentially you can use to like wait on the result of this job and actually get it once it arrives to you, right? But you can, for example, use it to like dispatch a bunch of those jobs and then wait for the results to come in. More excitingly, I think, the last 2 things are really much more interesting. So remote is, again, very similar to RPC Async. The only difference is that, it obviously executes asynchronously, but it also does not imply that the result will ever actually come back to the controller program. Instead, what it returns to you is a remote reference object. And those remote references are really, really interesting because they can also be passed around as, as regular objects, as arguments to other functions as well. And so what this means is that you don't sort of have this implicit data transfers, right, to the control program, and from the control program, you can just, whenever some function finishes on some worker, it will just store its result, and it will store its result as long as like any of the hosts in the host system contains a reference to that particular object, but the reference to this object can be shared, right? And for example, method calls on this object will become sort of tasks to be queued on the worker, which actually manages that particular object. So some use cases for this particular scenario are pipeline parallelism, right? If you can easily, using this remote reference, you can chain different tasks, and sort of you can by passing those remote references, you can make it easy to actually like build very complex sort of communication structures between different tasks in those pipelines. Also model partitioning. If your model does not fit onto a single computer or on a single device, you can easily like launch a bunch of processes. With this API, you basically write as if you were writing programming a single process, but now different parts of your model actually do the computation on different parts on different hosts. Then asynchronous parameter servers. This and reinforcement learning example actually makes use of a very interesting feature of remote references, in that you can actually create remote references yourself to the objects that are in your controller program. And once you create those references, you can also pass them on to other workers. And what this basically means is that those workers get a means to asynchronously call back to your controller program, for example, inform it about some progress, right? Or ask it about like the next actions to be done. And I actually have an example for reinforcement learning that makes use of that. So often in reinforcement learning, right, you have some agent and you want to train it to like make wise decisions about which action to choose in what circumstance. And you want the agent to basically interact with a lot of different environments, but maybe if the environments are somewhat expensive to simulate, you might want to like distribute the simulation over multiple different environments, over multiple hosts, right? So the way you write it in a single controller program, and again, like all of the code that you see here essentially lives in a single file. It's just the distribution, sort of the code that like actually that actually queues those functions, which will distribute the computation. So we have an implementation of the agent, right, which is a class with two methods: select action and receive reward, to sort of better inform the future choice of actions. And then, so at the bottom in the controller half, what you can see is that in the controller, we will essentially create the agent, we will launch a bunch of those experiments using the async call, and we will pass a remote reference to the agent to every single one of those workers, right? And then we will basically wait until all of those experiments complete. At the same time, workers, so this def run experiment is still, of course, in the single program. It's just that it will actually be executed on those workers, right? Because we sort of passed it to RPC Async. What each one of those workers will do is it will basically loop until the simulation is not complete, and as long as it is not, it will ask the agent, which lives in the controller program. So this is this asynchronous callback for the next action. It will simulate a step of the environment, and it will inform the agent about the reward. So this way you can easily, for example, create agents which interact with lots of environments sort of at the same time in a distributed fashion using basically a really tiny script, which I'm super excited about. Then finally, this is a bit more of a backend change. We're also sort of working on overhauling the backend for this particular single controller mode, right? The difference now is that previously we were sort of leaning on a lot of libraries that were designed for this collective communication, but this single controller model sort of makes more use of like a point-to-point communication. So TensorPipe is a new backend that optimizes point-to-point communication and also adds a lot of interesting features. Like it is topology aware. If a few of your processes are on the same host, it will not go through the network interface. It will just like use shared memory to exchange the data. It no longer requires full meshes, so that is better for fault tolerance. Whenever anything drops out, you don't sort of lose your whole network. A large part of your network sort of can stay untouched. And it also supports structured messages, right? So you can not only send like unstructured buffers of data, now you can also like ship, let's say, dictionaries with some tensors and some metadata that will explain you how to interpret them whenever the receiver gets them. So that is everything sort of when it comes to distributed updates, I think, in PyTorch. Just to close off, I wanted to share a few success stories, just to show you that we're not only doing good with research right now, we're also sort of getting increasingly a bigger foothold in the industry as well. So I have 4 stories to share with you right now. One on the left, you have Mars. Mars is a company that produces a lot of the well-known suites, and they're, for example, using PyTorch to do quality assurance as part of their production processes. Then a lot of the self-driving car companies actually also use PyTorch, and that group includes companies like Tesla. Then you can have in engineering you have Autodesk, so the makers of some very popular CAD software packages. They're actually using PyTorch to also sort of do semantic search for some parts that might be relevant in certain contexts. And finally, when it comes to translation, Duolingo, which is an application that you can use to learn foreign languages, they actually use PyTorch to sort of tailor the experience, tailor the courses to everyone, every single user individually. Just to finish off, some interesting statistics as a sort of health check on the project. Right now we have over 39,000 stars on GitHub, and we have over 1,400 contributors. Of course, we're extremely grateful to every single person there. We also have very active user forums. If you have any issue, you can just go there, and some very experienced members of the community will surely help you, no matter how simple or complicated your problem is. Those forums actually get like over 3 million monthly views. And if you count like all of the downloads from the official distribution channels for the package, that amounts for over 10 million downloads since the beginning. All right, so that is everything I have prepared for today. Thanks a lot for listening, and I hope you've enjoyed it.
Thank you, Adam. The COVID-19 pandemic has led to an explosion in curated data sets and scientific papers on epidemic modeling, epidemiology, and related topics. And that's what's making it challenging to identify trends or potential breakthroughs. Join me in welcoming Amy Heineke, the principal product architect at Primer. Amy will talk about the website they launched, COVID-19 Primer, which uses the latest advances in NLP technologies to discover trends in research papers and what they've learned so far. Please welcome Amy Heineke.
I don't need to start this presentation by telling you how much of a challenge this pandemic has been. We have all been living it every day. The scientific community has risen to the challenge at a speed that is breathtaking. This chart shows the growing size of the literature. We're now at well over 25,000 papers, letters, and preprints. The number's growing daily. But this chart tells us a lot of stories, of fast turnaround times, of doctors, of researchers who have spent their lives studying similar viruses and have now turned their attention to this one. And also of labs and of scientists who have completely retooled and refocused to rise to this challenge. This chart tells us about a mass mobilization, but there's also a catch, a growing information glut that is hard to make sense of. Life and death decisions weigh on the question, which papers do you pay attention to? Which do you trust? I work for an AI company called Primer. We use natural language processing and machine learning to structure large unstructured document sets and to summarize them to help make sense of them for people. When the outbreak started, we refocused our efforts and we built this public, free website in order to give people another way to explore this growing literature. We shared it with scientists, with researchers, with policymakers, and I hope that after this talk, you'll have an opportunity to go and explore it too, and I hope that you'll find it useful. Now, I'm going to spend a very short amount of time talking about how we built it, and then a longer period talking about the lessons that we've taken from building it. We started by collecting the literature. Firstly, we went to PubMed, which is a large collection of published, peer-reviewed papers and letters. These are from all kinds of different journals. We also went to the 3 preprint servers, bioRxiv, medRxiv, and arXiv. And we supplemented these with a stream of news and Twitter data, linking them up when they mention the papers by URL. We set up a process to get this every day, and we feed it through a pipeline of natural language processing, doing things like extracting people's names, extracting quotations, attributing them, resolving them, summarizing. And that's what gave us this site. Now, there's a number of different ways to explore this site, and I'm not going to talk about all of them, but I am going to show you a couple of my favorites. So firstly, we have a dashboard that gives you a view of the most recent changes. So what's new? We then have a fully automated natural language briefing. So this is generated without human intervention every single day. And it gives you highlights of recent papers that were widely shared and discussed. And my favorite feature on this is that we're able to find quotations by paper authors when they appeared in the news talking about those papers and show them alongside. We use classification to bucket the papers into major research categories. And we use an unsupervised topic modeling to discover emerging areas of new research. So, what did we learn from this? Well, this is going to be a tale of 3 parts: of confusion, of conspiracy, and finally, thankfully, of hope. Science is not a tidy process. It leaps forwards in fits and bounces, and especially in a pandemic, when the available data grows rapidly, as ideas are challenged, our best interpretation keeps on changing. This is a well-known researcher walking back his earlier findings on how the virus made its way to Seattle. After taking more samples, after doing more research, what they realized was there was another path that perhaps made more sense through British Columbia. This is how science is meant to work. But it does make it very hard to keep track of, to know the current status of each idea, and to weigh the uncertainty of what we know now. And that's especially difficult for policymakers who have to make decisions now. But this is happening at a time when the scientific process is changing. Preprints are new to the biomedical literature. So these are documents that are not peer-reviewed before publication. And instead, that review from other scientists happens in the public eye after they are shared. Now, this means that the research can be shared much more quickly, and a much wider set of eyes can look at them. And this is really, really good news in a pandemic where where time is of the essence. But it does make it very hard to know what to trust. So we've had preprints around for a long time in the mathematics and physics world. Archivers have been around for decades. But medRxiv, so in the medical space in particular, it's very, very new. medRxiv was only launched last summer. We're still figuring out the APIs. We haven't had time yet to figure out how to talk about these publicly. But they are a large proportion of the research. So 25% of the content on our site is from these preprints servers, and a third of the news talks about them. So they are very much in the public conversation. But this is also happening at a time when journalism is under duress as a result of the pandemic and of longer term changes and challenges. 40% of journalists in the US were laid off this year. 40%. That's a staggering number, and it means that there are far less people in newsrooms able to take the time to help us make sense of what is going on. And what does that mean? Well, here's a paper that was published in early May. In it, the researchers looked at samples of the virus that they took from different patients, and they compared them. They compared the genetic sequences. And what they found was that there were differences. There were mutations between them. and that some of those mutations, some of the versions were much more prevalent than others. So what do we take away from that? Well, the first interpretation is that this means that there is a newer, scarier version of the virus that is wildly transmissible. And maybe it means that things are different. We should be concerned. On the other hand, there is much more nuanced reporting that explains that possibly what we're seeing is just the result of chance. Some versions just happen to be the ones that spread further. So our interpretation affects how nuanced we think the science is and how much more there is to learn. But there are also less benign processes at play here. One of our findings has been that the most widely shared papers on Twitter are the most controversial, not the most useful. This paper, which was posted at the end of January, was at the top of that leaderboard until about the middle of May. In it, the researchers compared the genetic sequence of the coronavirus with the genetic sequence of HIV. And what they found was that snippets of the genome, the coronavirus genome, look the same as snippets of HIV. This they called uncanny. It begged the question, how did they get in there? Well, as soon as this paper was released, the scientific response was immediate and very harsh. Here's one example. An assistant professor of biochemistry from Stanford University, she said, the similarity is spurious, not higher than chance. As a result of this and of the overwhelming feedback, the authors withdrew it. This was celebrated as a great moment for science. And this is how it's meant to happen. Anyone can upload their research to the preprint servers. The scientific review happens, and if the science is found to be faulty, the paper can be withdrawn, and then we can all move on. Apart from if we don't all move on. We found that of the 42,000 tweets about this paper, 20% of them happened after the paper was withdrawn. And even now, if you search for this paper, what you find are tweets like this one, asking whether the withdrawal is actually evidence of suppression. These tweets feed into a wider conspiracy theory. How do we have these conversations about uncertainty, where our view updates, when there are people willing to jump on it and interpret it this way? So where do we find hope? Well, it helps to go back to this incredible chart. Science is marching on. We know so much more about the virus now than we did when this started. We know how it affects our bodies. We know how it's transmitted. And we have many more ideas about how to treat it. Science is a fantastic process for finding knowledge, even though it is confusing. It's a fantastic process because it works. But that doesn't help us answer the question of who do we trust? How do we make sense of this as we see it unfolding before our eyes? Well, the first good thing to look for are the people helping explain it to us. So great journalism is able to engage with the nuance and the uncertainty. This article from Ed Young at The Atlantic does that very well. There's no clear evidence, and there probably won't be for months. This is the article about that confusing mutation study that I showed you earlier. He's written a fantastic series of articles that explain some of the uncertainty that we have to live with as we walk through this pandemic. There were also a large number of scientists who are taking a lot of time to explain and contextualize the research that we're seeing. In the site, if you go and look for the people who are most quoted, you click on the numbers, you can read some of their recent quotes. One of my favorites here is Caitlin Rivers. She's able to bring her background in public health to explain what the path out of lockdown might look like. Here she is describing how Liberia handled the Ebola epidemic, and she's hopeful about what we can achieve now. So here it is. We should take time to explore and engage with this literature, and we should do so as optimists, skeptical optimists, engaging with this growing content and realizing that it's uncertain, but looking for the places where emerging scientific consensus is growing, where papers build upon each other, where the evidence is mounting. So what lessons can we take away from this more broadly, and especially for our work as data teams? Well, firstly, it's very good for us to reflect on the fact that this is the era that we live in, one in which information is abundant and easy to access, but one where we don't know why we are shared, the content that we are shared. Why do we see what we see? We don't know how it fits into a bigger picture. You and I could spend all day reading true things, and at the end of the day, not have read any of the same things in common with each other, and have a completely different view of what's important. That gulf between us is an enormous problem. It's one of the defining challenges of this era. But I do see some reasons for hope. We have a toolkit in front of us where we can do things like structure text, aggregate it, compare it, summarize it. We can do that at scale. Recent advances in natural language processing allow us to do it with much more precision than ever before. Recent advances in the infrastructure allow us to do it with a much greater ease than we've been able to do it before. And those to me seem like some of the building blocks that we need to be able to build tools that really support people's quest for knowledge and for truth. And especially for people whose job it is to make sense of all of this for us, whose time is tight and incredibly valuable. I think we have a real responsibility in this moment to see what we can do to bring to bear these technologies to make better sense of it. Thank you.
Thank you, Amy. This concludes our general sessions of the Spark and AI Summit 2020. Your feedback is important to us. Please take a moment to complete the conference survey in the navigation panel. And as a reminder, we hope you'll consider participating in our Summit donation matching program. Help us reach our goal of 100K. Thank you, and see you next year at the Spark and AI Summit 2021 in San Francisco.